So in this final section, we're going to look at predicting user preference or consumer liking using our sensory measurements, again using partial least squares. Why might we want to do this? Well, consumer liking tests are traditionally quite expensive and time consuming. It may be possible that if you can produce a accurate predictive model to replace this using cheaper sensory measurements. In this demonstration, we're going to show you how to do that, but we're also going to apply our model to our test data where the consumer liking is currently unknown. So returning once again to the partial least squares procedure, we go to tasks, of course, down to analyze, and then partial least squares regression. This time, of course, we're using the training data, but our predictor fields or input fields or X array, if you like, is these 12 sensory measures. And the thing that we're trying to predict is this single preference value. So it's only one field. We're going to restrict the number of components extracted to six factors, so six components. Ask it to identify outliers. Hit next, and once again ask it to standardize the data by dividing it by the standard deviation, and we'll do the same thing for our dependent variable here, standardize the data. Validation, of course, very important. Full validation switched on, and we're going to use the NIPALS algorithm before we finally finish and build the model. When we build the model here, we get again very familiar regression overview plots here, which will be shown, and once again we'll switch on our labels for them. Let's switch on the labels for them. Perhaps here we're seeing that factor 1 is distributing the samples about factor 1 and factor 2. Factor 1, interestingly enough, here is explaining 27% of the variance in our sensory data, but it actually explains 91% of the variance in our dependent preference, consumer preference field. So it's got the by a large amount, it's got the vast amount of the explanatory power, if you like, of the model. Factor 2, on the other hand, here explains 31% of the variance in the X data, in the X array, which is our sensory data, and only adds an extra 3%, at least using the calibration or training sample to the predictive power. Perhaps it makes more sense for us to go and look at the sample groupings here and change these so that we can see how they're distributed in terms of preference. So, and then click OK at that point. If we're looking at in terms of preference here, we can see that factor 1 does a very good job of discriminating between the low preference scores here from 1.8 to 314, which are in this dark blue group, and then the brown triangles, if you like, 716 to 0.85, very high scoring. So factor 1's doing a lot of that. A lot of the explainability here is really soaking it up and really discriminating. Factor 2 gives us a bit more explanatory power, and you can see that we're creating some nice quadrants here of groups, so it shouldn't be too difficult for a model to discriminate between them. Interestingly, if you score low on factor 1 and low on factor 2, then you're really in the lowest group. If you score low on factor 1 and high on factor 2, then you're in the kind of middling group here, 3. If you score just above factor 1 and close to 0 on factor 2, then you're in this 5 group, and then we've got this 4.48, 5.82 group, which is people who are scoring just above 0 on factor 1 but low on factor 2. So you can see how this does a pretty good job of discriminating between them. Also notice here that preference loads very high on factor 1. It's loading very high on factor 1. It only loads slightly higher on factor 2, so hence factor 2 only giving an extra 3% explainable power, if you like, to the model. And when we look down here at the explained variance, it's interesting that the calibration plot shows once again factor 1 maxing out at about 91%. Factor 2 barely increases it by about 3%, but when we compare and contrast that to the validation line beneath that, the validation line is indicating that really you should hold on to factor 2, even though it doesn't look like it's contributing much in the calibration. It's actually adding about an extra 10% in the validation. So, and if you add that, at least in the validation, you're getting close to about 80% or something like 85% or around about that number in terms of its explainability. If we look at the predicted versus the reference here, it's showing very, very high R-square here of 0.99 and 0.91. That's using factor 5. It selects that one. It's the highest R-square values. And our MSE value here, very, very low in our calibration of 0.17. Obviously, the smaller the number, the less squared error there is. We can switch this. If we click on that, we can switch this, of course, to factor 1. And we can, of course, add lines to it. We can put a reference line through that and show our validation and our calibration models and how well they fit our predictions. And then switch down through the relative factors, seeing the R-square value change in turn. So certainly at this point, it's looking like a two-component or two-factor solution is probably the most parsimonious solution, in the sense that we get the most amount of explainability with the minimum number of factors. And that's interesting to note. If we wanted to see the relative contribution of the variables themselves, there are different ways which we can do that. But if I go down here to regression coefficients, look at the series of plots, I'll probably get rid of the three-dimensional ones and just look at these line plots, which I'll convert into bar charts for you. And let's just get them similar. They look very similar to one another. This is the weighted regression coefficients, and this is just marked regression coefficients. So basically, these are the raw values that the model would use to make predictions. And because the values are quite standardized, you know, they're all within sort of standard units, they look quite similar. And these are the weighted regression. These are effectively the standardized regression coefficients, which help and aid with interpreting the model in terms of what is contributing towards preference. And what we can see is redness, very strongly related to preference. It's very positively correlated with it, as is color, as is sweetness, and as is chewiness resistance, if you like. Whereas negatively related to it is raspberry smell and bitterness, and at least it is on that particular factor there, which is factor 5. Let's look at factor 1. Okay, so we can see once again redness, color, sweetness. Here in factor 1, it's thickness, which is negatively related to the overall preference. And you can, of course, show all of them. Okay, it's also worth noting that these can be shown in numeric format up here in the results folder. You can go down to the beta coefficients weighted, showing the weighted beta coefficients. And again, you can choose the appropriate factor, if you like, and have it show those beta coefficients. This is a constant value here, so this is effectively a linear equation. And that's for the weighted, and the raw raw values, which of course the model's going to use to make its predictions, are shown here. And again, we can change the factors relative to that. Okay, having done that, maybe we should have a go at actually choosing this model and using it to make a prediction. So the first thing I'm going to do is I'm going to actually rename it. I'm going to call it preference PLS. And then if I return to the tasks menu up here, I can go now to predict and go down to regression, because we're using a regression model to make a prediction. Note that it shows PLS up here. That's the earlier regression model that it can see in the project, but it recognizes the fact that I've created one called preference PLS, and I can restrict the number of components that are going to be used. So we know that 2 components is probably the most economical number to use. And if I also switch on a few other options here to show the inlier limit and the sample inlier distribution, I can get that. And then of course I need to tell it what rows of data I want to apply it to. Well, I want to apply it to the prediction data. So we've got these prediction rows here, which are 8 rows of that, and the columns I'm going to use to do that, of course, are my sensory input variables. The point of the sensory input variables is that they should be used to predict preference on these 8 cases, these 8 samples, where we don't know what harvest they came from. We don't know what cultivars were used, but we do know how the panel actually assessed these 8 samples. And we click OK at that point. It then applies that model, and it shows us what it predicts to be the preference scores. And it shows the preference scores with a deviation estimate around it. So it gives us an idea of the reliability of that preference score based upon how typical that sample is relative to the data that the model was built on. So we can see here, for example, that there's more deviation around sample 7, indicating perhaps it's not as typical, and that it also happens to be a sample where there's quite a low score for preference. That the sample that seems to have the highest score for preference is sample 4, followed by sample 8, probably followed by sample 1, if we like that point. So there's other information here about scores and loadings that we can look at, see the various predictions. But if we wanted to get some sort of estimate, what kind of error rate can we assume we're going to get with our data? Well, if we return to our preference PLS model that we saw earlier on and look at the plots there. Here we've got our regression overview plots. If we go down to the explained variance here, this is explained variance we saw earlier on. If I right click on this and go to PLS and ask it for some variance and RMSEP, so root mean squared error prediction if you like, plots, and click on that. What that gives us is the 2 lines once again for calibration and validation. So there's the preference for calibration and validation. So if we switch that off and show just the validation preference here, what we can see is that round about a 2-factor model, you should be expecting to get an estimate with a deviation value on average of about 0.83. So it should, on a scale of 1 to 9, a deviation value of 0.83 is usually regarded as pretty good and pretty acceptable. So it is indicating to us that we could at least automate our consumer liking, our overall preference or values, and estimate that based upon the panel assessment scores. Hopefully that gives you a good overview of how you can use Unscrambler with this type of application. And here we've had a good deep dive into principal components analysis and how we would apply partial least squares.